So hey everyone, welcome back to my channel. This is Lakshay here. So today we're gonna start with our lead code question number 131, which says palindrome partitioning. So let's see what this question says. It says given a string S, partition S such that every substring of the partition is a palindrome, return all possible palindrome partitioning of S. So in this question we will be given a string. Let's say take from our example only AAB. So this is our string here. So we have to create all the possible combinations of the substrings we can create from this, and each substring should be palindrome. So let's see how can we can create it with how many combinations we can create. So first combination can be like this. If we separate them, then each substring is palindrome. You can see B is palindrome in itself, A is palindrome in itself, and A is palindrome in itself. Second combination what we can form is like this: AA and P. Now you can see that AA is a palindrome string, because when we read A from here and when we read it from here, it will give us AA only. And B is also palindrome string. So like this we can have our string, and these two will be the only possible combinations. Let's take, if we try to create a substring like this, okay, then it is not palindrome when, because when we read it from this side it will give us AAB, and when we read it from this side it will give us BAA. That's why this can't be part of our substring. So it's clear what we have to do in this question. Now let's see how we are going to approach this problem. So we will be given a string like this. So we will create an index pointer which will be at starting pointing to at 0 index, and we will try to create a substring. We will try to check palindrome from the first index like this. Let's suppose like this. So we will check for this index, and we will create a pointer like end on its next index, and we will call our check palindrome function for the index, like the for till index to end, which will be this array. And if it is palindrome, then we can check for further, okay. But if it is not palindrome, then we will simply return back from here. But if it is palindrome, then we can again call the function, and now it will check for the next substring like this. Now our index is here and our end is here. Now it will again check for this. Then if it is palindrome, then it will again call the function like this, okay, where our index is here and our end is here. Then if it is palindrome, then it will again call the function. Now our index is here and our end is here. So now it is also palindrome. Now when we again call the function, we can see that our index is already equals to a size of our string. That means we have to return from here, okay. After this we will again return from here. When we return from here, we can now what we can again another case we can perform from here. And what is that? We can now take two string from here, okay, because at first time we were taking one string, but we already knew that there cannot be another cases, like our end is already pointing here now. So when we our end moves, because we have to move our end on every iteration, after it comes back we can see that our end can't move further, okay. So that's why we can't create more substring here, so that's why it will again return. But when we reaches here, there is another chance of creating a substring like this A, and instead of taking BB separately we can take it as like this, okay. So now our index is here and our end is here. So now we'll check if this is a substring, it is a palindrome, then we can simply add it to our resultant vector, and we can check that now our index is now pointing to the next last position. So it will be added and it will return back from here, okay. Similarly we can check for this here also, that instead of separating A we can try this combination, okay. If this is palindrome, then we move further, but it is not palindrome, that's why it returns back from here, okay. Then simply like this only we can take another combinations when it returns here. we can check for this also, like AA slash BB, that if this palindrome, then we move further like this AA BB, then again further, then returns back, then again another combination can be like this. So this is how we can try all the combinations. Okay, now let's write down the pseudocode so that you will understand more clearly. First of all, our main function. Okay, this will be our main function where we will be provided a string. Okay, first of all, we create a vector resultant. This will contain all our resultant, means all the combinations we will store finally here, and this will contain any combination we are forming. And now we call our backtrack function, and what we will pass here, definitely our string, our index which will be 0 at starting, our path, and our resultant, that will be our final answer. And at last we will return our resultant because it will contain all our combinations. Okay, cool. Now let's see our backtrack function. Same, our s, our 0 which will be called as index, then our path and our result. Okay, so first of all we will check if our index is equals to a string size. That means we have already reached our limit and we will simply return from here. But before returning, we must push our value result dot push back our combination that we have formed, which is stored in our path vector, and then we will return. If not, then we will start our loop like this. We will create a variable end which will be pointing to index plus 1, which means next index, and it will keep on iterating till our end is smaller than equals to our s dot size, like this. Okay, now what will happen, it will check that if a substring from index till n minus 1 is palindrome, then only we will move further. If, let's suppose we are having a function palindrome, it will check where here will pass our string and our left pointer, which is what is here, we know index, and a right pointer which will be end minus 1. Okay, so it will check if our substring is palindrome like this. We are going to pass our substring like this, we are passing this, like passing this. So it is will check that if it is palindrome, then what we will do, we will definitely push it to our path. It means path dot push back our substring. What was our substring? S dot substring from index till which what length. Now we will have to write the length. So our length will be, our substring length will be end minus index. This will give us our desired length. Okay, which we have to pass to our value. Let's see how this is working. This is working like this. Our index was here and our end was here. So now we know that our index is at 0 and end is 0. So how this is deciding our length? This is deciding like index minus length was 1 minus 0. So it means index minus 1 means we will start from index and only of length 1, means we will only take our substring of length 1. So this will give us only a. Okay, if it was 2, then we have got a, but this is only 1, so we got a, and which was the original substring which we have passed. Okay, so after getting this, what we will do now, we will call the backtrack function for the remaining sub problems. Means here we know that we knew that a is a palindrome, but now we have to check for the remaining now. That said, we will now pass the remaining values like this by calling a backtrack function, again passing our s. But now what we will pass, we will now pass our end here, and then our remaining values, that is path and our result. At last, when the backtrack functions comes back, the most important step is pop back, because we have to pop to make a recursive tree Good. Okay, so this is our only function. This is how backtrack is working. Now let's write our what palindrome function, because it's also very important. That is bool palindrome. We were having three parameters here. First was our string, and then we are passing a left pointer and a right pointer. Okay, these were our left and right pointer like this. Index was our left pointer and -1 was our right pointer. Okay, then we will check that while a left is smaller than right, we will check if our s means our strings left is not equals to strings right, then we can directly return from here false. That means the string is not palindrome, because we are trying to read it from the left and right, means both the ends, and can see that they are not matching. But if that's not the case, we will keep on iterating like this. Left will plus plus, right will plus plus, and after this while loop ends, means if this while loops completely iterates and now our left is not no longer smaller than our right, this means that our string was palindrome, so we will return true. Okay, so that's it. This was our pseudocode. This was our backtrack function. This was all the stuff you needed. That's how we are going to approach this problem. That's it. So you must try this recursion by yourself, that then only it will be clear in your head. Okay, so now let's discuss the original code which I pasted below. Here it is. So it's same like I told you. This is our main function where we are creating our resultant vector and a path vector, and we are calling our vector function, and at the end we are returning our result vector. So here is our vector function which is called, where we are passing our index and the stuffs that we already passed here. Then we are checking same if the index is reached to the last string element. That means that we have traversed whole the string and we can definitely push it back. But if that's not the case, that means there are more elements remaining. That's where here we are traversing them. Then here is a checking some function which is checking that if our string is palindrome or not. If it is, then it is returning true, but if it's not, then it is returning false. So that's it. Now let's discuss the time complexity. So the time complexity will be big O of n cross 2n. And why so? Because big O of n is the time it takes to check our palindrome. So you can say that it's for palindrome check, and to the power n is number of recursive calls. Okay, because this can be the number of combination we have to check. Like this 2 to the power n was here, it was 2 to the power 4 means 16, and our string was something like this a, B. So we have to check so many combinations. Like first of all we can check like this if we take them separately. Then if wait a second, we'll explain it. If we create this combination, and if we have to create this combination, or if we take this whole string as starting, or if we create this combination, or if we create this combination, there are various combinations. So that's why we are done 2 to the power n recursive calls. Okay, that's why our time complexity is this. Now let's talk about the space complexity. So our space complexity will be I should write it here. Big of n for our recursive stack, big of n for our path vector, and big of n cross 2n for our resultant vector. Okay, what I told you for recursive stack, this is for your path vector and this is for your resultant vector. So you can say it like this: space complexity equals to big of n cross 2n. Okay, so this is your space complexity and this is your time complexity. Okay, so that's it. This was your code, this was your question. I hope you understand it. Okay, so we will see you in the next video. Till then, stay tuned. Thank you. Bye bye.